Hello everyone. Let's get our webinar started. Welcome to our Open Power Academia and Research webinar once again. And thanks for joining today webinar. And my pleasure to have you all here. And I have Abhishek, who is a collaborator, for this special group as well as special initiative to work on using, the Power Core, which we opened recently, and also the Open Power ISA. We also have our special speaker and my colleague, Vinod from IBM India, to provide a detailed presentation on Power and Open Power Processor and its features. Today's session will be recorded and shared. Question and answer will be end of the first, the session, and also people will be allowed to speak also. You can raise your hands as well as you can post questions in chat window. Abhishek, go ahead and start your, presentation. uh, the great initiative from you.
Yeah, uh, so I'll share my screen.
Sure, please. Thank you for joining.
So, can you all see my screen?
Not yet. Oh, yeah, it's
Yeah,
coming up. Yep.
yeah. So, yeah. Now you can see.
Yeah, go ahead,
Yeah.
please.
Hi, I am Abhishek Zadav. I'm an undergraduate. I'm an uh, yeah. So I'm an undergraduate student from Father Conseco Rodrigues Institute of Technology, Vashi, Mumbai. Uh, uh, like uh, Telling about my background, I come from a tier 3 college in India. Uh, my uh, uh, my uh, my uh, my interest towards computer architecture came into when I was in second year. Uh, and it took me quite a time to research more about this domain and start some initiative. Uh, so uh, basically, basically in this lockdown, I used my time to work on my LinkedIn profile by writing uh, b- by writing articles and consistently posting about high performance computing and computer architecture. Uh, I uh, 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 it, so So it took me 2 months to actually reach where I am right now. So I'm going to tell you about my project today, but before going to there, I would like to tell that some of you may think that doing this may be difficult at a student level, but coming from a tier 3 college and and working on this, I would like to tell that I was on the same boat where you are right now, 2 months back, and I didn't actually know I didn't know anything about open source architecture. So now going into the project, I will tell you the basic question that we all that comes into our mind is why Power ISA? So uh, why Power ISA is that because the main question is there are other popular ISs that we know, like ARM, or we also know or we also know uh, uh, we also know uh, so basically Power ISA is a risk-based architecture. So what happens in here is for us a particular task, for a particular task that we want to perform, like multiplication. So risk will take more instructions to perform, but they are simple to use, unlike we have a sys with us. So uh, so uh, uh, so what makes it different is that it is completely open source. uh, it is completely royalty free. So many of you have already studied about 8086 by Intel. So basically, it is a proprietary uh, uh, ISA, which is not completely available. Most of the ISA is actually proprietary with them. So being a student or an academician, we do not have that a scope to even work on this ISA. So uh, coming into what this project is all about that I'm going to talk about is we have to basically create a processor using Power ISA. Uh, I would like to tell you something that already has happened. Last uh, a month at the uh, Linux Foundation Open Source Summit, the OpenPOWER Foundation announced that they are going to uh, 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 they are going to open source the ISA that is uh, 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 they are going to open source a power processor core that is uh, uh, A to I. So talking more about this, we can actually build this targeting uh, into signal processing. We can go into HPC. We can also go into AI/ML. So talking about this, I have already. So I would like to tell you that in the recent conferences on supercomputers, the researchers see the future of high performance computing development in software hardware co-design, which can be done using Power ISA because it is completely open source. It is completely free. So it is easy to build on such ISAs. And today, ISA is gaining popularity because because I have already told you of some points on that. We can target this on. So I would like to tell you that on 25th on July, a DAC conference is there. They announced that in 2018 they had only 56 submissions on artificial intelligence hardware, and now in 2020 there are 194 papers on this. So we are actually seeing that there is a huge uh, a, a huge development we can see in this field. So what makes this project different is that the code that IBM has or that has recently open source, that is you can see that is uh, uh, A to I. So this is such a powerful core that we can even go building supercomputers. Yeah. So what as a student, where do I see this project going? So there are two answers to this question. One is we can create this processor core, and we can support it to the uh, other popular ISAs that other popular codes that are already available in the open source. Or the other thing is that we can commercialize it because currently it is completely open source, and we don't have to pay a single amount to the Power ISA. So we can create this a processor core, and we can even commercialize this. So basic advantage of this is uh, I, if you have seen the proprietary ISAs that are currently popular that we can see in our mobile phones or laptops, they are completely proprietary by their company. So as a student or academicians, we cannot use that because that is not completely available to us. But looking at this free ISAs, we know that this complete ISA is uh, is available with us, and we can go up to building supercomputers at our level. So the last thing that I would like to tell you that we actually need more people to come up and build their course on Power ISS, because it's completely free, and you don't have to pay any charges. And at the end, I would like to say that Power ISS has scope that we can only see we can only see that into coming years, and even now there are many companies that already been I would like to tell you that I would like to tell that in Barcelona, a supercomputing center, they actually announced uh, 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 they actually announced in the month of June that they see the future of high performance computing I are using this Power ISA because this is completely free, and and I would like to say that if this is completely free and if this is the future of what we see uh, in artificial intelligence or in high power computing, high performance computing, I guess we need more people to come up at our level, that is student or academicians, and we can go up to building supercomputers. So thank you so much.
Yeah, Abhishek, thanks for your wonderful, talk on, your interest as well as how you want to take it, and do some work on this project. I am inviting all other students as well as the developers in India as part of this, the initiative. Everyone will get an opportunity to speak this kind of webinars, and we also host, several international webinars also. You will get to know what's happening, in Europe and in US, countries, and the processor development and all those stuff. This is a great avenue for you to learn about the complete, the stack for developing a processor. And and also, as Abhishek said, we had a the power core which we open sourced called A2I, and also we open sourced last year in August the Open ISA. With these two things, people can definitely learn a lot. And also we are working on developing a curriculum. Probably you will get an opportunity to see the curriculum too, um, in addition to what you are working on. And it's a great platform for you to grow your skills and get into the latest and the greatest the processor technology development and testing. And now I'd like to invite my colleague Vinod to give a presentation about the processor, the power processor introduction, as well as he is also going to touch upon some details on the Power ISA as well as the A2I. Vinod has been part of the IBM's India software development for validating next generation processor, which is actually P10. That is also going to be announced pretty soon, in a month time, in one of the key conferences in US. The earlier worked on validation development software for previous generations too. The processors P7, P8, and P9. As you all know that the P9 processor is actually one of the we have used the processor to build the top 2 and 3 right now, the supercomputer, even the top 9. Or there are a lot of supercomputers built using P9 processor. And also the P9 processor enabling many enterprise servers too. Like for example, locally in India, the Airtel kind of companies, and also globally many telecom companies and banking systems are all using the Power 9 processor. So that's a kind of the very active processor where you will get skills on it. I'd like to invite Vinod to start the presentation here. Welcome, Vinod.
Yeah, thanks Ganesh, and thanks Abhishek for the initial talk. I'll just share my screen.
Yeah, looks good, Vinod.
Okay. Okay, I'm going through the power architecture overview. I am basically talking about the basics of the architecture so that, when you guys want to go through the Open ESA or Open A2I, the ones which are made open by the power process, by the IBM, you will be able to understand. So this is like a power basic architecture overview is what I'm trying to cover in today's session. Okay, so what does the full form of power? Power means performance optimization with enhanced risk, and AS stands for application system. Coming to risk is reduced instruction set architecture. So as you all may be familiar, there are two types of architecture predominantly in the industry. One is RISC and one is CISC. So power architecture uses RISC, and then power architecture supports both the formats of Little Indian and Big Indian. And we have three variants of the operating system in general, which are running on power processor. One is AIX, other is IBM I, and Linux. So these are the three variants which we run. And primarily AIX and IBM I use Big Indian, and Linux uses Little Indian. So power architecture is 64-bit. There was a time when it was 32-bit, but the current 64-bit architecture is backward compatible. So it still allows 32-bit applications to run in 32-bit, or 64-bit operating system, and obviously the 64-bit applications can run. And in the 64-bit architecture, all the registers in general are 64-bit wide. And we have a different ISAs for each of the implementations which have happened in the past. Like P6 was based on 2.05 ISA, and P7 was on 2.06, and P9, the one which is in the market is 3.0B, and this is the one where IBM made it open source. So I'm just going through the basics here. I'm just starting here. So the OpenSI, if you go through, there would be book 1, and that's where you will start, going through the basics of the architecture. So there are different category of instructions that are present: branches, load stores, fixed point unit, FXU, binary floating point, BFP, decimal floating point, DFP, vector instructions, and then there are some combination of vector scalar instructions. And when it comes to RISC and the power processor, all the arithmetic operations are between the register to register. So they do not go to memory. Only when there is a load and a store, the instructions will access the memory. And there are some special purpose registers like condition register, count register, target address register, link register, floating point exception register, floating point status and control register, vector status and control register. So these are the special registers which are used. So when some instruction is executed, the condition register, you can compare with the result, whether it's greater than, less than, equal to. So that's where the condition register is used. And count register is something used with the branches where, you can have some counter so that you can branch off depending on the counter. Target address register is a special kind of a branch instruction register used. So I'll cover that in later charts. And most of you may be familiar with the link register. Link register is something like you make a function call, you want to return back from the function, or you can return to the function. Link register is internally used so that you can do those programming concepts. And then when you do some fixed point operations, you can get some overflow, underflow, those kind of stuff. So that's where fixed point exception register is used. Then FPSCR, floating point and status control register, is about floating point operations. So here too there are various control and status registers which are present. So which will indicate what my floating operation happened for the current instruction. And similar to floating point and fixed point, we do have a vector status and control register. So coming to branches, we have a different kind of branches, conditional and unconditional. When it comes to conditional branches, there are relative branches and absolute branches, and then branch instructions which will end with an L. So when you go through the ISA, you can see that when some branch instruction ends with an L, it's basically using a link register. So when it'll branch off, it'll save the current address in the link register. So that you can, when after that function call is done, you can branch to link register and come back to the place from where you have begin. It'll actually store the current instruction address, the next instruction address, so that you come back to the place, to the instruction after the one you did a branch. And there are conditional branches. So the conditional branches, there are different conditions, depending on which conditions takes place. So there is a PO field in the instruction which will determine, how the branch should happen. So there are some hint bits, whether branch should be taken, whether it should not be taken. So there are a lot of combinations which are there, which are all described in ISA. So coming back to the condition register, so it's basically 32 byte wide register. It basically has 8 4-bit fields. So there's something like CR0 to CR7. So CR0 is one register which is implicitly used by some instructions like stux or lux, or these are basically some lock instructions. So when you go and do a lock instruction, whether the lock is successful or not is recorded in condition register. And there are some transaction memory in the operations or instructions where to CR0 is implicitly used. So briefly touching upon transaction memory. Transaction memory is instead of logs, you can have transactions. So there are special instructions which are present in Power architecture. So instead of taking a log and then multiple threads, software threads or hardware threads, looping on a log, you can do it in a transaction. So it will replace the locking mechanism. So that feature is present in Power architecture. So there are some instructions associated with that. And in general, CR1 is implicitly used by floating point instructions, and CR6 is used by VMX instructions. And remaining CR fields, you can mention if you want, explicitly which CR field to be used. So those would be used by other instructions. And there are some instructions where you can manipulate the CR. So CR and, CR NAND, CR OR, CR NOR. So those are some instructions where you can do that. Then move to and move from CR instructions are also present. I'm sorry. Okay, then count register and target address register. So count register, as I said, that is something you can do when branch on a count. So this can be imagined by a for loop, right, or a while loop in our programming. So you can do a for from say I to 10. This 10 can be part of the count register. So every time you can do a loop, you will increment the count, and when the count register your condition is matched, you will branch out. So that kind of support which is there from the architecture. And then there is a target address register. So this is a TAR, which is called. So this is something similar to count, but it only holds the branch target address, and you can just branch to that instruction. And link register, I touched upon it. So basically link register is mainly used for subroutines, calls and returns. You can save the place where you want, from where you are going in the link register, and you can come back. And then there is microarchitecturally a lot of work done in optimizing. Branches are one thing where the performance of the processor is dependent on. So there is microarchitecturally a lot of work which is done, how to decide whether a branch is taken or not, whether the conditions happen or not. So that's where there is something here. You can see they are talking about link stack. So there is a stack where they have all the LR values they are taken till now. So they will be able to basically tell if a branch happened, whether you can take it, all of that sort. So BHRB is something where the history of the branches are kept. So you want your program not to depend on that history of the branches that has taken because you are running a different program, or you want to do an optimization or stuff like that. There are some instructions which will clear the contents of the BHRB. And then you can also read from the VHRB to know, how like trace back what branches were taken. So this can be used in debuggers and stuff like that, which can give you the track of the branches that are done. Next is fixed point instructions. So these are all register to register instructions. So there are different type of fixed point instructions. Like you can do add, subtract, multiply, divide, and or rotate. Trap is something, you do some operation, it'll take you to a interrupt handler telling that you got a trap. Then you can deliver a random number. And then there are instructions where you can do a move to and a move from GPR or other registers like vector registers or floating point registers. So we have 32 general purpose registers, and each of these registers are 64-bit wide. And and then something about fixed point is a fixed point exception register, as I earlier mentioned. So there are different bits in it, overflow and carry bits. So whenever you do some operation, if there is an overflow, that bit would get set. If a carry happens, carry bit would be set. And then there are some bits. There is a tax active concept I wouldn't cover in this session, but that's something which happens in the power architecture. Moving on to floating point overview. So there are different kind of floating point units that are present. So there is a legacy one which has been coming from previous generations, that is binary floating point. So single precision and double precision formats are supported in this floating point unit. And there are 32 floating point registers which can be used by these instructions. And all the binary floating point instructions start with the letter F. If you are going through the ISA architecture, you will be able to easily tell all the instructions which start with F, are BFP. And then there are vector instructions, which are single input and multiple data. Single input and multiple data. So these are VMX instructions, and all of them are V only supports single precision, and there are 32 VRs, and all of these instructions begin with the letter V. Then we have decimal floating point, and in decimal floating point, there are, in addition to 32-bit and 64-bit, we do have 128-bit operands, and these registers also, operate on the 32 floating point registers which are there, but they operate it as 16 pairs of quad word registers or quad word length registers. And then there is another unit called vector scalar extension, VSX. And then here too, we have single precision and double precision instructions. And the vector scalar extension are like more of a graphical kind of instructions, which will help if you want to use those kind of applications. And we have, and VSX has its own set of registers, and there are about 64 VSRs. Okay, so that's a brief introduction about, if you are going through the open instruction set architecture, different units, different registers that are present for each of these units and the branches which we went through. So coming back to what was discussed earlier by Ganesh and stuff like that. So there was previously, OpenPOWER Foundation. Through OpenPOWER Foundation, Power ISA was made open, and there is a link to it which I have put here. So using that, you should be able to download Power ISA, and this is based on 3.0 version, and this is what is used in Power 9. And all of the architecture stuff, be it branches or different units, the ones which I described and much more is present in this ISA architecture. And then this is the basis, depending on which you can make a processor. So this is like a Power ISA is like an instruction set architecture, and you can implement a processor depending on this architecture. So A2I is one such processor where it uses the ISA version 3. It uses ISA version 3.0, the embedded version of it, and then IBM has made open all of the, it has made open the specific architecture it has used in A2I, and it also made open the RTL code and all of that stuff, and then the FPGA help which is required. So that is all open, and then you can access all of that links using the link I've pasted here. So this is the basic introduction I wanted to touch upon. So if there are any questions or any interest in any of the area, I'll be able to take those questions.
Vinod, thank you for your presentation, Vinod. And thanks a lot. And I'd like to ask the participants, anybody wants to speak here, and so that we can share the platform. There are like opportunities here to collaborate, and that's where we are going to work on it. Maybe for the next several webinars related to the processor development. We can use this as a platform to collaborate and to exchange technology and all the stuff. So we know there are questions people are asking right now. One of the questions is actually Mega from Mega. She's asking, can you please shortly describe any use case?
Use case. Yeah, so the Power ISA architecture is something which is the architecture which is made open source, and you will be able to, if you are into the processor, you want to make your own processor, you will be able to make your own processor depending on the ISA architecture. So A2I is one such example, and then there are in OpenPOWER, if we go through that site, there are various examples where a lot of systems have been made using this architecture, right? So can you specifically tell, what is that you're looking for, use case, meaning the main use case is you can make a processor out of this, you can base it on this particular architecture. Is there anything else you are looking there?
Yeah, maybe I will allow her to talk actually. That would be a nice one. Megha, please go ahead and respond to Vinod's question.
Yeah, hi Vinod, I'm Megha here. Thank you for answering. And I was interested in how beneficial will be to use this architecture in AI applications. Are there any distinguished advantages, or something which is different from the existing architectures here, so that the use in machine learning or AI comes handy? That was my curiosity. Thank you.
Yeah, that's that's a good question, Megha. So thanks for asking. So if you see the Power 9, it is used extensively for AI and machine learning. So internally, the different units I've mentioned, will help us in writing code which is optimized for machine learning and AI. So there are a lot of vector instructions, and then the floating point instructions, and then other kind of operations, and it being reduced instruction set architecture. So all of this will help us in writing a lot of optimized code, and there are a lot of benchmarks with IBM and Power Processor, where like for P9 we have a good results, like you want to run your AI applications, machine learning applications. So if you can read through, like for Power 9, it is extensively used in machine learning and AI, and that's a proof that this particular instruction set architecture helps you to get the performance benefit there.
Yeah. Thank you for that thread.
Megha, can you introduce yourself? Actually, I just want to know, like, who are all attending,
I am Mrs. Megha Kolekar, and I am working as associate professor with Father C. Rodrigues Institute of Technology. I came to know through Abhishek about this event, and I immediately joined. I didn't know anything about ISA. So I joined to know about this work that is going on. And my main interest is in machine learning and AI.
Oh, nice. Thank you, Megha.
Yeah, sure. Thank you.
Yep. And uh, any more questions? Okay, we'll make more interactive also here. I have another the guest student. Shivam Poddar. He is ready to talk and share some of his experiences and what he wants to do with this. Shivam, please go ahead. Oh, hold on. Yeah, I'm giving him permission to talk. Shivam, you can talk
Yes,
now.
yes, am I audible now?
Yeah, go ahead, please.
Okay, thank you so much for giving me this opportunity. Hello to all the attendees. I would like to thank Ganeshan sir, Abhishek, and Vinod sir for giving the presentation on power. It was really apt and to the point. So, actually, I haven't worked much in power yet, but I have interacted with Ganeshan sir a bit on LinkedIn. To tell about myself, I am a final year undergraduate student at NIT Surathkal, which is in Mangalore, Karnataka. And currently I am a GSOC student with FOSSI Foundation, which is basically free and open source Silicon Foundation. They work on a lot of things, in the direction of open source hardware. So that's a really good thing, which is happening in the community and the industry as well. That we have multiple open source initiatives which are taking shape. Uh, as uh, as we have heard already, Power is one such initiative. Then RISC-V is another one, which is really making good progress. Although Power is something which is already industry proven. It is something which is already used in server architectures, and now IBM has open sourced it. RISC-V is something which started as an academic project and is now going to a stage where it would soon be silicon proven. Although there are some chips are coming out, but it is there are still a lot of things to be taken care of. But the good thing is that since such technologies are opening up to the community, they are no longer restricted inside the company. Then students like us or people from the academia can look into those projects and try to learn something. And as my GSOC project, I'm working on open source RISC-V core. The great thing is that the ISA itself is open source and the core itself is also open source. And the language stack which we are using is also open, is also new technology. Instead of coding it in traditional system Verilog or Verilog, we are using something called as transaction level Verilog, which is basically a timing abstract representation of Verilog. For example, those who would have worked on pipelining of processes or something similar, it would be, it is really a painful task to retime those circuits or to ensure that, all your control logic is staged through your pipeline and you are implementing it as expected. So in this case, tail Verilog comes into the picture and it takes the abstraction level to a higher point where you really don't have to bother about, explicitly flopping your signals and things like that. And the best part is it gets compiled to industry standard syntax in system Verilog. So you can build new logic in this new language and then integrate it with what you already have. For example, a future use case might be integrating a new logic written in tail Verilog with the OpenPOWER core, which sir mentioned about. And there are a lot of other areas in open source which are opening up. For example, as Megha ma'am asked for the deep learning accelerator, there's a open source microarchitecture released by NVIDIA, which is called NVDLA. You can find it on GitHub. It is basically just a accelerator core which you can pair it up with any processor, write a proper interface for that, and accelerate your applications on that. So just getting the A2I core itself opens up a lot of opportunities for people in the open source community to work on it and build out new projects. Apart from NVIDIA, I would like to also mention a new initiative by FOSSI Foundation and Google, which is basically about building open source cores right to fabrication. I mean, till now, most of us would have seen RTL being open source, the Verilog code being open source. But now we have reached a stage where you can build open source fabricated through those initiatives. I would share the link in chat. Those who are interested can surely take a look. Yeah. any questions or anything you would like to discuss?
Yeah. Yeah, thank you, Shivam, for wonderful share actually. I think you covered a lot of stuff, what's going on in Europe and in US, as part of Google and all the latest, the greatest stuff in the open source world for the, the hardware. This is very good, I welcome you again, to collaborate on our platform and see what we can do, together, to take it further. And even India has got initiative, national, the processor initiative. I'm also, discussing with some people, to see how we can, take this as a part of that initiative too. So probably like, people like you, the developers and, the faculties, the professors and researchers, and also the industry specialists, if they all, share some of their, the thoughts and, and experiences on this platform, definitely, this would take up a, new venue for building, uh, a processor with it, like a make in India kind of, the goal also we can have. There is a possibility for that too. Good. Thanks for, sharing that. And any more questions from the audience? Looks like there are questions already answered by Vinod. And any other questions people have?
So, sir, I'm Sundar here. So I'll go ahead. I hope I'm audible. So thanks for this. Yes.
Yeah, go ahead, Sundar, please.
Yes. Thanks for this initiative. It was a great presentation by Vinod and Abhishek. So thanks for it. Thanks for introducing to the new ISA. Like this is new to me as such. So I've played around with Risk V, but this is something new. I'll go check the links out because many of the things were like the kind of new things that I saw just today. So one of my question was that, so you described ISA for architectures. So I think that was answered by the previous talk where he mentioned about this compatibility with previous Verilog codes. So whatever Verilog codes already been written is kind of compatible with OpenAI's output. I was thinking of accelerator that can be done with the help of this, not processor based, but something like a co-processor or hardware accelerator based on RTL design that can be integrated along with OpenAI. So how feasible is it, and like can we design it in OpenAI itself without the IAC? Right? Is there support for that, like accelerators as such, not a complete processor?
Yeah. So as part of the open power, there are other open some things which are for accelerators which are made open. So can you check on CAPI, Open CAPI? That's one accelerator, that will help you to even that's open source. All of the stuff related, all the documentation and stuff related to it is open. So you would be able to do an accelerator, FPGA kind of stuff using that. Open CAPI architecture, and that's part of the open power.
Okay, sir. Thanks a lot. Thanks a lot.
If you want, I can type it in here. Open CAPI.
Yeah, and also that is actually part of our invitation logo too. Open Power and Open CAPI. So you can look up that. And we do have a lot of presentations about Open CAPI too. If you want to learn more about it, and even if you want to get access to that, we can provide access to for the Open CAPI. We have servers installed in US. And Parikshit, do you want to talk? I see you raised your hand. I'm going to allow you to talk now.
Hello?
Yeah, go ahead, please.
I'm from CDAC Pune.
Oh, thank you for joining. I did announce that to CDAC also. Thank you for joining. Yep.
Yes. We have several initiatives internally on RISC-V and Open Power as well. But I am new to this area, so I wanted to ask about that, and Vinod answered my question.
Oh, okay. Sure.
So if you want, I can, for others, I can reiterate.
Yeah, please go ahead. That would be nice too.
So my question was related to RISC-V core architecture, which is also open source, and compared to that, what advantage or why my decision should be based on this architecture. So from server class processor development point of view, I think this instruction set architecture is richer than RISC-V. That is more towards high-end embedded applications, you can say. So that was kind of a response from Vinod. So I think that answers my question.
Yes. Thank you, Parashit,
Yes, thank you for the
for
opportunity.
sharing. Yeah, thank you. Any more questions, team? And also you can share, what you want to hear, going forward, as part of this group. We have a group also created by Abhishek, a LinkedIn group where you can join and collaborate. And also there is a WhatsApp group for this, and you can join and collaborate. Abhishek will send you the link and the slides, after the presentation. And, and also we will put together kind of, a joint, kind of a virtual platform, where people can, collaborate, even hardware building and all the stuff. Why not, I'm trying to see what are all the other academic institutes in India are willing to, work with us so that we can put some hardware, related to this, and, people can go and, build things, on top of that. And, I think this platform is going to help you out a lot, for your, career, as well as, opportunities, worldwide, on this power technology, as well as the open, the hardware technology, because this is the only active system right now, well open, from the processor to the application. We have, the open ISA, and we have the open core, and we have, the reference board, the reference design for the motherboard, where you can create a system too. And we have, the abstraction layer, the OPAL, and, the Linux also supporting as part of, this ecosystem, Red Hat as well as Ubuntu. Why not? You can have a complete, a stack of, the open hardware, and start creating, edge computer, the edge based computer. We all know that the 5G is, going to be dominating, India in a year time. And, for that, there are a lot of hardware, edge based hardware required. And this could be the one, can go on, do edge computing. And also we can build, high performance computing, and also the enterprise class computing too. So this is a great opportunity for all of you to, collaborate on this platform. Any questions before we close this call? Abhishek, you want to have a few words actually before closing? Abhishek?
Yeah. So I would like only I would like to tell that we need more people from India who would actually collaborate in this, and and because this is a free and open source, I say the thing that is happening is currently currently this industry doesn't have many options going through, because if you see like the embedded systems that we have, uh, uh, the Moore's law is also being there are many problems in as well. So so only being an open source, we also have this as a license free. We can commercialize this, and we as a student, or academicians, we can even build our startups. And because of this, the market will get a wider range of processors that they have, because right now we don't have much of option that we see in the market. And probably uh, uh, as a student, what I see is that this will go a long way, and we need more people to collaborate with us. Yeah.
Sure, Abhishek. Thank you very much. Your initiative, as well as, your presentation here, I really appreciate it. And I am welcoming, other students, researchers, and partners to be part of this, collaborative platform. For the next webinar, or maybe a workshop we can arrange, a full day workshop also we can arrange. We have been doing that, in Europe as well as in US. And I would like to thank the presenters for the presentations today. And also thanks to all the participants who actively participated and really shared, some of the people, really shared their experiences too. And looking forward to meet you all for our next webinar, which will be announced shortly. And thank again, and I'm closing the webinar now. Thank you.
Thanks, Ganesh.
Thanks to you all. Yeah.